Hello! Today, as part of our study of the motion of a thrown body, we will consider the motion of a body that is thrown at a certain angle to the horizon, and we will consider what basic principles we can use to describe this motion. To begin with, let us present a model of such motion in the figure when we have two coordinate axes along which this motion will be performed. And the initial velocity of the body will be directed at some angle to the horizon. Let us assume that this angle is theta. The trajectory of this flight will be some kind of parabola which has an ascending line, and then a descending line. If we look at such a motion, we can observe that relative to the top of the parabola, the upward motion will be completely repeated in its downward motion. Thus we can solve problems taking into account this knowledge. When there is a speed with which the body moves along the x-axis, there is a speed with which the body moves along the y-axis, and further, breaking this motion into two components, we can easily describe it. Let's do that. First, let's look carefully at the initial velocity, and we see that it is directed at some angle to the x-axis, and we can in this situation consider the projections of this velocity on the corresponding axes. To do this, we again drop the perpendiculars to the x and y axis, and we get the components of the initial velocity along the x-axis and along the y-axis. Thus, having found these velocities, you and I can tell how the body moves along the x-axis. And here it is necessary to remember once again that the acceleration of free fall, which is present in such motion, is directed vertically downward. That is, it is directed along the y-axis and has nothing to do with the x-axis. Therefore, our task will be to consider the motion along these axes and tell that the body moves along the x-axis uniformly and along the y-axis with acceleration g. Let's write an equation that will show the dependence of the coordinate of the body along the x-axis, given that this motion is uniform. The value of the final coordinate will be determined with the corresponding equation, which we know very well. We derived it at one time in the equation of uniform motion when we studied it in our topic, and accordingly we can immediately use it in this problem. If we look carefully at the projection of velocity along the x-axis, we can see that this is the adjacent cadet in the resulting triangle. Now let us substitute the value of the projection of the initial velocity on the x-axis. We have obtained this expression. If we combine the origin of coordinates with the point of throwing this body, then we can say that the initial coordinate will be equal to 0. It's easier to solve the problem. Then we will simply define the value of the final coordinate by this expression. But this is again a special case. We will mention it immediately in the problems. What happens to the motion along the y-axis? We will define the value of the final coordinate along y from the point of view of the equation of equal variable motion. Let's write down this equation. The final coordinate on the y-axis is the initial coordinate on the y-axis plus the projection of the initial velocity on the y-axis times the time of motion. And immediately we take into account the direction of acceleration of this body, that is, it is directed against the y-axis, so we put a sign of minus. And we get this expression. If, of course, we have again the initial coordinate on y will be equal to 0, that is, we combine it with the point of the sample, then there remains this expression which we will further analyze. We make a substitution for the velocity projection. We put the initial coordinate for now. The projection of velocity along the y-axis will be equal to b initial multiplied by the sine of theta angle multiplied by t and minus t squared by 2. So we have two equations that can describe the solution of this question. With the assistance of these equations, we can determine and describe various parameters. These include the duration of the body's flight, the distance covered during the flight, and the height of its ascent. All of these factors can be analyzed comprehensively using the system of these two equations. It is important to remember that the velocity of the body will vary at different points along the trajectory. This variation is vital to consider when evaluating the motion of the body. The velocity vector at this position of the body, let it be some finite velocity, it will consist of two components, one of which is the x-axis velocity. It doesn't change during this motion. And the second component is the velocity on the y-axis, which is exactly the variable component. In the process of motion it changes, and therefore the total velocity of this body changes too. To solve this question, we see that this velocity is a diagonal in a shelf rectangle, so we can find the final velocity as the sum of the squares of these two components. From which we know the initial velocity, respectively its component we have x, but the final velocity along the y-axis we can express with u through the equation of equivariant motion. So to do that, we use the equation of velocity. Again, taking into account the sign of acceleration, which will be directed against the y-axis. Solving these systems in complex, we get the possibility of finding a huge amount of parameters. For example, let's consider the task of finding the time of flight of a given body, if we know the initial velocity and the angle at which the body is thrown. We can consider this motion from different points of view, but the most convenient way to consider the situation is from the equation of motion along the y-axis. You and I know that the body was thrown, for example, from point 0, that is, let's take the initial coordinate of this body as 0, and this body landed again at the same coordinate, that is, on the y-axis, its initial and final coordinates are 0. So we just supply here the value 0 instead of the given coordinates and write down what we get. We've got this expression. Now we can process this expression in terms of some mathematical principles. In particular, we see that we can reduce the time t, that is, divide the whole equation by the same value of t. And we are left with one unknown time of flight of this body. If we get an expression for it, it looks like this. A ready formula to calculate the time of flight of a body. If we want to find the range of flight of a body, we can substitute this formula into the value of the coordinate of this body and get a formula to calculate the range of flight of the body. Given, for example, that the initial coordinate will be 0, the value of the final coordinate can be easily calculated. To do this, the initial velocity multiplied by the cosine of the angle phi and multiplied by the time of flight, which we have obtained here. You and I can see that the product of the sine, cosine, and 2 has appeared in this equation, and this is nothing but the sine of the double angle. We also see the product of the initial velocity, which gives its square, and then let's write down the final value for this coordinate. The initial velocity squared multiplied by the sine of the double angle and divided by g. Actually, another formula that can also be used as a ready-made formula for solving many problems. I will see you in practice, where we will apply these equations and see the peculiarities of motion of a body thrown at an angle to the horizon. This is the end of our lesson. Goodbye, everyone.